it. Okay, I will then send you the link just afterward. I was just thinking you probably have better certainly overview who's participating. Okay, so I will also do this as I do in the teaching. I will just be writing or using my iPad. Okay. That is, do you see it now or?
Yes.
Okay. So maybe I should hold it. No, that is even worse. Okay, so I should actually say we had a seminar before, so during the time as LSU was open, before everything closed down, where I was actually talking about exactly those things. This is very much related to the work that I have been doing with Matthew Dawson and Raul in Mexico. Both of them are now in Mexico. And I actually started last semester and gave, I think, 3 talks. And it turned out there were a lot of graduate students, so it was a little slow maybe. But what I want to do, even if I already started talking about it, I will still actually, because there are several new people here, kind of go over the first, even the things that I already discussed, okay? So what I will be doing is somehow just introduce the basic parts and then go into representation theory. So what we have been doing is actually try to figure out and prove theorem how one can use representation theory in the theory of Toeplitz operator. That would be in complex analysis operator theory. Okay, and in particular, what we have been doing is, okay, can one use the representation theory to say if an algebra of Toeplitz operator is commutative or not? Can one use the representation theory to construct abelian C-star algebra? Okay, and then if you have an abelian C-star algebra, then the algebra has a spectrum, or each of the operator has a spectrum, you say eigenvalues, and what we want to do is then use also the representation theory and some group theory to calculate this spectrum, figure out actually what the eigenvalues are. Okay, so this is the main thing actually, that is to use representation theory to solve problem in the theory of Toeplitz operator, and in particular theory of abelian C-star algebras. And C-star algebra, I did introduce it the last time. Those are, say, just operator algebra that are invariant under the star operator. One can define this in general, completely abstractly, but our C-star algebra will always be concrete. What is important is that the norm condition that if one takes x star x, then this is the same as the norm of x squared. And a typical example of this is just the bounded operator on a Hilbert space, okay? So this is really a very beautiful class of star algebras and are very important in a lot of application, particularly physics, for example, non-commutative geometry and other things. Okay, so what is the setup that we will be looking at? What we will be looking at is a domain in Cn. So this is an open, simply connected, really set in Cn. Okay, and this is open. And later on, we will assume that we have a group acting on this set. Okay, and then we have a probability measure on M. One can discuss if it is really necessary to have a probability measure, but that is what one usually assume. And then one has the L2 space. Okay, so in particular, all of this L2 spaces contains just the constant functions, and it actually contains all the bounded function. And because it's a probability measure, we know that LP is contained in LQ if P is greater or equal to Q. And then what we look at here then is a Hilbert space, H in the L2 spaces, and all the elements of H are supposed to be holomorphic functions. Okay, and we can define holomorphic function. For example, you think of the Cn as just R2n, so you have a differential, you have the total derivative, and the condition being holomorphic is that you actually have a complex linear map, which is just in every variable you have the Cauchy-Riemann equation. And in most of the cases, we have the Hilbert space that we take is just the space of all holomorphic functions on M, which are square integrable. This is actually then a closed set and space. I will maybe talk a little about that. And the important assumption that we want to have is that the point evaluation maps, just we evaluate the function at the point set, that this is a continuous linear functional on the Hilbert space. Okay, so here it is really just needed that we are looking at the space of continuous function. We cannot think about all the L2 function because there is the point evaluation does not make sense. Okay, but if you have a space of continuous function, then you can always ask if this is a continuous functional. And the good thing with this is, I should say also, this is a condition that is really made a lot of times. So for example, if you want to do, say, sampling theory and things like that, you have to have this condition because otherwise, I mean, you have no control over the values. This is, say, if the points are close, then really, okay, that is wrong what I was saying, but this gives you something that is continuous, okay? And this is always the case by if you have a measure which is actually absolute continuous with respect to the usual Lebesgue measure. So you have a function h which is a continuous, and I forgot to mention here actually say this function is supposed to be, say, continuous, but the important part is it is always bounded away from 0, okay? So one can locally divide by this function. And that means then actually in particular, if you have a compact set and the function is bounded, and 1/8 is also bounded, okay? And I think I showed that in the seminar in the spring actually then, by doing this locally, by integrating over a small disk. First you integrate just over a circle and use the Cauchy-Riemann. You do that in each and every variable, so one can just reduce it down to the one variable case. So you integrate over a small circle, then you just get the function back again if you divide by 1/2 pi using the Cauchy-Riemann. Okay, so this is independent of the radius. So you can also write actually what you have, the value is the same as, okay, you integrate to pi and then you have to put r, okay? Then you get the function and now you also just use the Minkowski and you can actually then integrate the absolute value of the function squared times the volume of the circle, and now you can estimate the, okay, and then you would have to compare it by actually multiplying the function, okay, so I should not say actually you use the Minkowski on 8 and 1 over 8, okay? This is where this condition comes in. This is bounded, so over this disk it has a finite volume, and the other piece is just the norm of the function restricted to this disk, and you can estimate that by estimating over the full domain, okay? So that shows us actually that the value of the function on this disk is bounded by some constant times the L2, okay? So,
can I ask you a question?
Sure.
So you have a condition that h of z be positive.
Yes.
And that means strictly positive, right?
I mean strictly positive, yes.
Okay. So,
because you see how so I am dividing here.
Yes. Now, so this actually, there are, this is a certain, I'm just trying to make a connection to these spaces called the de Branche spaces, which are, I guess, quite different. That they're still reproducing Hilbert's kernel Hilbert spaces, but they're on the whole plane, but you just take the L2 norm on the line.
Yes,
like
that is also
different thing, completely different thing from what's here.
Yeah, I mean, what is important is actually then the reproducing kernel, and whatever the norm is, that is some kind of integration.
Mm-hmm.
So you can always actually compare the value of the function, for example, by comparing it with this integral that you can handle. But in principle, what is enough for you is you can do this for kind of arbitrary Hilbert space, okay? Yeah. The integral does not have to be given by an integral. You can just do it for arbitrary, there is a reproduction kernel Hilbert space, okay? Okay. But it has then to be a space of function on a set, okay? So I should maybe mention this actually in a moment. I did also talk about that in the class. But okay, so let me maybe wait with that. So what is important is that actually in this construction, you have a uniformly bound for the norm of those functionals on every compact subset, okay? Which is important in some proofs. But what is really important for us is that this implies, just by the representation theorem, that the value of the function at a point Z is given by an inner product, okay? So we get a function here, which is actually a holomorphic function, okay? But it is a family of a function and indexed by the element in this manifold, okay? So this will be an over-determined actual system of bases, kind of. That is how some people think about it, okay? Because this integral that we have here is, the f is given by this integral, okay? So, okay, maybe better to look at it in this one here, okay? So one thing, as if you have a basis, you can then actually write the function as the sum over those bases. Here actually you have a continuous sum, okay? And this is called the reproducing kernel for the Hilbert space, okay? So in this function is completely determining what space we are in. Okay, because the function kz is in the Hilbert space, then we see if you put in argument omega in here, you get something that is holomorphic. As I write it, actually one has to remember this complex conjugation in there. Okay, so the step from the function of two variable to function of one variable. But because of this, what we get here actually the first variable, see the first variable is here the index. Okay, and then we conjugate it. Okay, it becomes holomorphic in the first variable and anti-holomorphic in the first one. And the anti-holomorphic simply means actually you look at the opposite complex structure, or you can also think about the function is anti-holomorphic if this function is holomorphic, or if this function is holomorphic. It does not matter which one, okay? So that would be a definition of anti-holomorphic. Okay, so one reason why this is also important, so if you have this is a function on product of the domain, and if you have a function of two variables on the product, then this function is completely determined by the value on the diagonal, okay? So kz completely determine the function. Okay, I can explain that if you want to, but you just have to let me know. And I think we have the chat also up here. No, we don't have that. In case of people want to write something or ask for an explanation or something. Okay, what is also important is now you have this function, and this function is just k, okay, subset omega, but with a conjugation. But k subset is in the Hilbert space, so that is reproduced by the inner product. Okay, we have the complex conjugation, so what we get is the inner product between those two functions and then complex conjugation. Okay, if you flip the inner product, then you have to put in a complex conjugation that disappear, okay? So we get now kw set. So flipping the value of the in the function variable just gives you a complex conjugation, okay? So another thing is that this function is what we call positive definite. And that simply means if I look at it, what this is really saying, if you look at the matrix, what is it? Set J, set I. This is a matrix, a n by n matrix for every n. Then this matrix is positive semi-definite, okay? Because what stands there is really the matrix applied to Ci and inner product with this vector C1 up to Cn, okay? So it is non-negative because you just write it down. This is an inner product between those two vectors. And now you take this one in here, you take this one in here. Okay, so you get the sum. And this is just the norm of this finite linear combination. Okay? And that is non-negative. Okay, so let me then say another thing, actually, because we were talking about that. Actually, what is really needed is, if one is really doing analysis, then one looks at those reproducing kernel, or this positive definite kernel. That is just a function of two variables, okay? So that it is positive definite. It simply means that this sum here is always non-negative, Okay, so in particular, if you put then set in there, take just n equals to 1, just 1 point, then you get something that is non-negative. And we will always assume it is positive by throwing out the point when this is 0. Then what you can do is you can actually look at the space which is generated by those elements. Okay. Now on this space you get a pre-inner product by just defining this way. Okay. You define the inner product of the function this way here, and then find that linear combination. This is a pre-inner product. It might be 0. You divide out all the vector of length 0. Completed, you have a Hilbert space. And this Hilbert space is a Hilbert space of function, just by construction. And it has a reproducing kernel, and the reproducing kernel is UK. Okay? So the positive definite kernel and reproducing kernel Hilbert spaces, there are bijection between them. Okay? And this is one way to construct Hilbert spaces of function so that the point evaluation is continuous. And as I said in the lectures of the spring, this is not a restriction because every Hilbert space is constructed that way. If you have a Hilbert space, then you always have a very natural kernel, KVW. You set is just the Hilbert space itself. This is the inner product. By definition, it's a positive definite function. If you do the construction, you get the space back again. Because this linear combination, you can just take that into the kernel and you get actually something in the Hilbert space back again. Okay, so every Hilbert space is constructed this way. But usually what one tries to do is you choose special reproducing kernel, for example, holomorphic or what other property that you are looking for. And the nice thing with this then always points down to, you might start actually with an abstract Hilbert space. You get this kernel and you are just studying functions, really very specific functions. Okay, and another property is that you can, for whatever orthonormal basis you take, you can write this kernel up as a sum in this way. This is just the element of the basis that show up there. What we know for sure actually that is that, okay, now let me just change this. If you look at this function here, this is a function that is of the form some Cj depending on omega, and then you get your orthogonal basis. Okay, you take now the product with Vj, all the elements in the sum disappear except the one. Okay, and this one that is left is just the Cj, but taking the inner product with the reproducing kernel, just reproduce the function. So that tells you that this is Vj omega. Okay, you have to be careful where you put the V in and you get the bar. Okay, and then one knows that the point evaluations are continuous. Okay, so if you put in set here, then it is the same as putting the set n in each of the variables. This is maybe not a kind of a completely correct proof, but this is the idea, okay? Another thing that is important now is that we have this Hilbert space of holomorphic function which is sitting in a big L2 Hilbert space, okay? And then what you need to know is what is the projection down to the spatial holomorphic function, and that is just the integral against the reproduction kernel. Okay? One way to see this in an easy way is, you always know that if you have a orthogonal projection, then you just have to take an orthonormal basis, and what you get is this one here. Okay, this is the orthogonal projection. And now you just look at the form up here. Okay, what are you doing? You are just taking the inner product with the reproduction kernel. Okay, so that is one proof actually that you get this for the orthogonal projection. This is not only correct for L2, it is actually also correct for LP functions. Okay, if one is studying things like that. Okay, so this is somehow just the basic surrounding that we are looking at. And now comes the definition of Toeplitz operator. Okay. So what a Toeplitz operator is, okay, you take a bounded measurable function on M, and then on the L2 space, you have a multiplication operator. Okay, it's a bounded operator with norm less than or equals to the infinity norm of phi. Okay, so it's bounded. This is really the only place where one looked at the reason you take an infinity function. That guarantees that you have a bounded operator, but you could also take other class of function, even distribution, and you will probably just get a densely defined operator. Okay, or even also depending on the property of the measure, it might even end up being a bounded operator. But this makes it absolutely sure without having to think about further properties that this is a bounded operator. And now what you do is, okay, you have the Hilbert space or holomorphic function is sitting in the L2 space, so you take the holomorphic function, you embed it into L2 space, you multiply, and then you project back, okay? So this is really kind of what you would say, it is the projection, it is the multiplication, and it is the inclusion map. Okay, all of those maps are continuous, so this is a bounded operator with norm, again, less than or equal to the infinity norm of phi. And phi is called the symbol of the Toeplitz operator. And you can then write it down because we know what the formula for the orthogonal projection is. It is just the integral against the reproduction kernel. So this is really a fundamental formula because from this one can prove all kinds of properties of those Toeplitz operators. This is an integral operator. It's an integral operator and the kernel is phi times the reproduction kernel. Okay? Okay, and then it is pretty obvious that if you take the star of this operator, or what is a star of a linear map, TUV is just UT star V, okay? And then if you put this into the integral or whatever, so you see you get this extra conjugation, okay? Because it's a real measure, so if you conjugate the integral, also you can conjugate that inside. And if you move the Toeplitz operator over here, then you are multiplying, so to say, of the other side. Okay, so if you are actually with a holomorphic function, then the holomorphic function does not bring you out of your Hilbert space because we are taking all the holomorphic function. Otherwise, we would have to be a little careful, okay? So the projection is just the function back again. So in this case, it is just the multiplication operator. But if it is really not a holomorphic function, then it moves it out. So you have to project it back again. Okay, so why are Toeplitz operator interesting? So first of all, I mean, quantum physics, so you have these mechanisms to quantize functions. The classical mechanism is described by looking at functions, but the quantum mechanics, you look at operator. Okay, so the original philosophy to quantize was you have a function that represents a classical physical system, okay? And then you quantize it to become an operator. And it was really the question how to do it, because the problem is, for example, here, so one has to be careful about the order, okay? Functions as a multiplication is abelian, so it does not matter what you do, okay? Z bar, so Z and omega bar, so those are the same as omega bar and Z. But if you look at operator, you do not get a commuting algebra in general. So then suddenly the order matter, okay? And there are a lot of different kinds of quantization. For example, you symmetrize it, so the order does not matter, and then you quantize it. All kinds of things. I don't want to, no, you quantize and then you kind of look at the symmetric operator coming from it, okay? But anyway, you have then a family of operator, and then the bounded operator are a C-star algebra. So you look at the smallest C-star algebra that contains all those operators, okay? All the T phi as phi runs through L infinity, okay? That gives you a algebra, C-star algebra, which usually is quite big, okay? But you can also do a different thing. You can also look at a subset. Does not even have to be an algebra. You look at just a subset of bounded function, and you look at all the operator coming from that algebra, and then you look at the smallest one. One usually kind of assumes that B has the property. It is not necessary, but if you have phi, then phi bar is in there. That is somehow because then T phi star is also a Toeplitz operator because that is this one here. Otherwise, one has to kind of add the star, all the adjuncts to it, because one of the part of the definition is that the C-star algebra is a star algebra. If T is in there, then T star is in there. So there is no loss of generality, just if you have the B's, you can add to that all the complex conjugates. Okay, and then we get usually a smaller one. That is the TB or T sub B. Those are the C-star algebra that is generated by this subclass, okay? And one thing that one should somehow remember then is if you have B1, a subset of B2, then T of B1 is clearly a subalgebra of T of B2, okay? Somehow, so what we will be interested in are abelian ones. So if this one here is abelian, then the smaller one is definitive also abelian. Okay?
May I ask a quick question?
Sure.
Yeah, you have not fixed the domain yet, right? You're
no, this is
working on
just an arbitrary domain.
an arbitrary domain.
Yes.
Okay,
So
good.
then in a moment, actually, I will start to talk about the domains.
Okay.
This is just the general setup. This is the philosophy. This is what you do. And then you start to look at bounded domain, the CN and all of that. Okay.
And then a small addition to when you talked about the projection, how it extends to LP. I guess very little is known. Actually.
Yeah. Okay.
Okay.
That is. I was thinking about the bounded domains.
Okay, that's fine. Yeah, just wondered.
Okay. That is very little known, but yeah, okay, I don't want to say anything. Okay. So the questions, the problem is then, as I said, the original what that we were thinking of was the abelian algebra, because somehow people in C-star algebra were trying to find example of abelian C-star algebra. Those are really the nicest C-star algebra. They have a nice spectral decomposition. Those are really the nicest one. So they were trying to figure out classes of abelian one. What kind of condition do you have to put on this class B to guarantee that you have a abelian C-star algebra? And there are also then questions as, okay, what kind of condition do we have to put on the algebra of Toeplitz operator to get actually that it is generated by some class of function, okay? Then as soon as you have a abelian algebra, you want to figure out the spectrum. It can say it's the space of maximal ideals, etc., or the C-stars or the star homomorphism. And then, okay, this would be one of them. So that usually involves some kind of Fourier transform. One thinks, there is the theorem that says that if you have a commutative C-star algebra, then this is nothing with one. Okay, and because we have a bounded opera, so measure, then one has, in most of the cases, the function one is always a Toeplitz operator, okay, by taking just the constant function phi. One has to be a little careful now about this generating set B. Usually we just assume that the constant function is also in there. So the theorem is that every commutative C-star algebra is nothing but a continuous function on the spectrum. Okay, and the map is the so-called Gelfand transform. Okay, x of f, f hat of x. Okay, I was messing this up. Okay, evaluated on a homomorphism is just a homomorphism applied to f. Very tautological things, okay? So, but it is some kind of a Fourier transform. One can really think about the Fourier transform that way. So one tries to implement that if you have a abelian C-star algebra, okay? So here comes the examples, okay? So there are mostly two kinds of domain that we will be looking at. First of them is just the full complex space. And the measure that we do is the Gaussian. I should say also one can really do this much more general by looking at the heat measure, okay? Those Gaussian, really, the heat transform is just convoluting with the heat kernel, which is a Gaussian, and that becomes a unitary map from one of those Hilbert spaces L2 with Gaussian measure. No, let me see, one has to be a little careful here. I should not say it, I would have to recall it actually, but the image is this Fock space, but it depends on the parameter, okay? Or you can also think about it, you put the H in here, okay? One thinks of this as the Planck constant, which is kind of the inverse of the temperature, okay? So one can do it more generally than what I am doing here, but we will not really be going into that. So the Fock space is then the space of all holomorphic functions which are L2 with respect to this measure, okay? And this is, as you see, also we have here this density. So this is a reproducing kernel Hilbert space. And I will write down the reproducing kernel in a moment. But this is the first place where we actually see a density like this, which then guarantees that this is a reproducing kernel Hilbert space. But one should see actually, if we look at the density, what is happening as if you move to infinity, then this is going to become 0, okay? So as you start to do this estimate, what I did in the proof, then the constant, if you look actually at a disk with a constant radius, then this constant is going to explode, okay? Because you are getting integral over a function which is getting closer and closer to, you're looking at the reciprocal, so the function is growing to become infinity. So there is no uniform, those functions are not uniformly continuous. They're only uniformly continuous in general on a compact set. But then actually as the compact set is growing, then this constant is going to grow to infinity. And that is definitely going to choose some analytical problem, also in estimates and things like that, okay? So, because everything in there is kind of a product, this density is just a product of the one-dimensional case, then a lot of calculation can be reduced to that. And this is one of those standard calculations that one has to do. You look at z to the power n, you know that every function, holomorphic function, has an expansion in terms of z to the n, okay? But you don't know if that is the expansion in this Hilbert space. Now we are not looking at the pointwise, we are really looking at this in terms of the Hilbert space, okay? So what about that actually? Is this a basis? And the answer is yes. You do the calculation and you figure out the norm, okay? And in all of those, actually the typical thing is you actually use the polar coordinates. That is the reason that you get this +1 here. And then from the 2 pi, actually you get the pi disappear, and you have 2. But now you make the change of variable. You say u is r squared, and then 2r dr, so that is the expression for du. So both the 2 and the extra 1 disappear, and you get just the gamma of n + 1, which is n factorial, okay? And that really leads to the statement now, if you do it in higher dimension, because now z is just a product of the z1, alpha 1, z2, alpha 2, etc. The integral becomes just the product of the one-dimensional cases. You get that the norm of z to the alpha is square root of alpha factorial. And then one has now the statement that e to the alpha, e sub alpha, this is an orthonormal basis for the Fock space. And now one way to figure out what the reproduction kernel is, you use the theorem that the reproducing kernel is just the sum over this orthonormal basis. And just you see, if you look at this in one dimension, then you are just looking at Z times V bar, W bar, raised to the power n divided by n factorial, which is the exponential function, okay? There is a little more combinatorics involved in the higher dimension, but you get the same thing, and here is a missing omega bar. So the reproducing kernel is an extremely simple function. It's just the exponential, and you put in the inner product. Okay, this is the dot product, so this is also just E, and then you have the inner product between those two vectors. I think in this actually, because I might probably need that, the dot is just the usual bilinear form. Okay, so here is then an example, one of the important example of Toeplitz operator that Nikolai Wasilewski and his collaborator looked at. Okay, we let us just actually do the one-dimensional case. You look at all the symbols with a rotational invariant. So actually you have the torus, the complex number of length 1, which is just U1 acting on the C, the complex plane. And you look at all the functions that are invariant, and those are just functions of the absolute value. Okay, so we look at the symbol which is rotational invariant, which corresponds to function on L plus. Actually, the closure of L plus because the 0 is in there. Okay, and now you look at what this operator is doing for the basis, and you write it down. The basis is just the omega or wk, and you have to divide by the square root of k factorial, and then you integrate that against the reproducing kernel, and this is the measure. Okay, what is important now, you actually know this is rotational invariant, and this is rotational invariant. You use this symmetry to actually use polar coordinate, and in the complex plane, this is the other polar coordinates, okay? Now you can take the symbol, you get actually R to the power n, so you take that power out, and you also have then the power of L. You write down the formula for the exponential function, and then you have the e to the r squared. And now you can actually take the sum outside because everything converges nicely. And what you get there is you have all of those bunch of functions depending on r, and then you have the exponential. And now we know if the exponent is not 0, it is a periodic function, the integral is 0. So the only thing that survives the integral is the case where k is equals to n. Everything is 0. And what we see is we just get the function back again, and then some number, okay? Number that in principle you give me the symbol, then you in principle can iterate it, okay? So it is really a simple integral. So what is this telling us? This is telling us that, that all of those basis vectors, I thought I had actually stated it there, but I was probably just thinking, all of the basis vectors, they are eigenfunctions, they're eigenvectors, okay? So if you use this basis, you just get a diagonal matrix. And diagonal matrices, they commute, okay? So we get a commutative algebra, okay? And what is more here, we actually have a formula for the eigenvalue, which is the spectrum, okay? And what we are seeing here actually, which is kind of this basic thing, is we have a group acting on the manifold X, and then we look at invariance of those symbols. So what we're saying, we can choose the group as we just want to, and then we use the invariance to split up the integral, okay? And we have some kind of basis that is adapted to this invariance, okay? And then we can kind of use the splitting of the integral by saying something about the Toeplitz operator. So this is one of the philosophy. Okay, so maybe just before I finish, let me state what this result is, okay? So I mentioned actually that the commutative C-star algebra with 1, and this is definitely one of them because the constant function 1 is rotational invariant. Then we have this base of continuous function or compact set. Here we do not have actually the eigenvalue, we get a function now. The symbol depends on k, so we get a function on integer, which is far away from being continuous, okay? But we can still say something. So we take a metric space, and we say a function on the space is uniformly continuous. If, okay, we all know what it means, you have epsilon positive, then you can find a delta. So if the distance from x and y is less than delta, then the distance between the value is less than epsilon, okay? And we know what a bounded function is, and then we have the uniformly continuous bounded functions, okay? If f is a uniformly continuous and bounded function, then so is the complexification, conjugation. If you multiply them, they are still bounded and uniformly continuous. The sum is, this becomes clearly a C-star algebra, okay? So this is a C-star algebra. And the norm is just the supremum, okay? And then actually the statement that Nikolai proved was, and I think he had a co-author, was that, okay, these functions are eigenfunctions, the C-star algebra is abelian, and we can calculate the spectrum of the operator. And moreover, if we put the square root metric on the positive integer, then this Toeplitz algebra of the rotational invariant functions is nothing but the uniformly continuous bounded function on n. And actually, Vishwa has done some generalization of this. Okay, so what I wanted then the next to do that was to talk a little about representation theory, and then exactly how the interplay between those two things, somehow exactly what I said, how one can use invariant symbol to construct a abelian subalgebra, C-star algebra of Toeplitz operator. And there are tools from representation theory that actually produced commutative C-star algebra that the C-star people had never really thought about. So it turns out that this was a very powerful tool, and it also gives some kind of a mechanism with some extra condition how one can construct the spectrum. Okay, are there any questions? I think I will just stop here. No question?
I don't have a math question. May I ask a question? So you're giving a long series of talks on this. I may have arrived a little bit late for the introduction because my computer was slow to
Yes.
come up. So you have a couple of lectures planned already for.
Yeah, so what we are planning is at least 2, but also I want to avoid to be too fast, so I would guess it will end up being 3.
Yeah. Oh,
and what I am planning is, I don't know, maybe I should kind of post it on my webpage. I don't know, so Visva, do you have the email address for everyone? Or anyone has to know exactly who is participating? Because I could also email. Okay, so first of all, the lectures are recorded. So we can send out the link to the lectures.
Okay.
And we need to know who is participating. So the best thing is that the people that are not from LSU, or that way everyone maybe, just send an email to Isvaria to let her know actually that we should send the lecture notes to this address.
Okay.
I think that is probably the easiest way, because then we have the email address and we know who was there.
If I'm already on the list, do I have to tell you to keep me on it?
You're on the list.
Yeah,
Okay.
we already have the list.
All right.
Yes. So I should say also, my graduate students are organizing it. They are the official organizers.
So thanks to them for including me. I appreciate it.
Okay. Yeah. So, and we are really hoping that other people from outside of LSU are also willing to give some talk. So my extent actually to hear what other people are doing. But one of the reasons is, Visva and maybe Khalid, they are working on Toeplitz operator, but there are really no good basic references for that. So I'm also including just some kind of basic ideas about Toeplitz operator for them. Okay?
Yeah. This result now, the last one, the theorem, it's a V. I did not quite get the name.
Oh, that is Nikolai Vasilevsky.
Vasilevsky.
Yes. I have to admit, I certainly was not sure how to write the name. So I decided,
Okay.
I think I know it, but I decided as, okay, I would have to check on it to make absolutely sure how it is written and who the co-author was, so I just was lazy. That is, if I was talking at a conference, I would definitely write it out completely.
Yeah. Okay.
But he is one of the leading people in the theory of Toeplitz operator, and he is, I think, from Ukraine, and is now located in Mexico City. That is one of the reasons that Mexico is actually very strong in Toeplitz operators. More questions?
Are people applying this stuff to potential theory yet?
I actually do not think so.
It really sounds like there could be something there.
Yes, I think it actually has potential elsewhere, but somehow most of the people that are in the theory are C-star algebra people.
Yeah.
So they are studying this, actually the K-theory and all kinds of other things actually.
Yeah.
And
I'm just trying to make connections to that, because you know how in potential theory and de Bruijn spaces, you have Hilbert spaces on some large, you have analytic functions on a large space, but then the whole measure and the reproducing kernel are on some boundary. The integral is over a boundary, and you're reproducing like functions that are like analytic or harmonic in a larger space. And so much of it is the same. But
yes.
somehow I don't know about those multiplication operators and
yeah, I would somehow think about that in a little different way. Actually, I mean, if you look at the board, just or the disk, then you have the reproducing kernel, but you also have the Cauchy-Circuit or the Poisson transform from the boundary into the circle.
That's correct. Yes.
Yeah. So those are kind of two different things. But in many of those actually things we will actually see that later. Actually, representation theory somehow tells you how to construct integral operator that kind of reproduce the Hilbert space from L2 of some smaller manifold. Usually not the boundary, but I mean, the problem in general in the situation is the question about the existence of the boundary values. For the disk, it is easy, but then you have actually some kind of a hard disk space or something on the boundary. Yeah. Yeah. And then you get a map that moves it inside.
I was going to ask about that. So there's this Corona theorem that talks about the spectrum of, say, the holomorphic bounded functions in the disk.
Yes.
And is there something similar in this more general context, or?
As I have formulated now, I would say no, because the set that I am looking at and so far has no structure. Okay, it is just a bounded, no, it's not a bounded, it's just a domain in Cn. Okay, so we don't know anything about the boundary and things like that. But if you are looking at, say, the what's called the bounded domain, actually, then you have some kind of Poisson transform into those spaces that we will be looking at. Then you can kind of look at boundary value, and you can look at map that takes us from the boundary into the Hilbert space. This is really very important in some applications. In this Toeplitz operator theory, I would say I have never really seen it used there because the just bounded function, actually, you have no idea about the extension of those actually to the boundary. And
yeah.
Sure, if you have a unitary map, then you can transfer those operators to something on the boundary. But I am actually thinking there is some recent work by Uppmeyer and one of his collaborators, which are actually using the boundary. Okay, I cannot say exactly what it is, what they are doing, but they are actually using the boundary of bounded domains. So there is some connection there, but I haven't really I've just seen those papers, and I do not really know so much about what they are doing. Okay, more questions? Okay. If there are no more questions, then we can just...
Can I just